So to translate these in words, what the fixed diffusion says is that the net movement of a solid is equal to the product of the diffusion coefficient, which depends over the properties of the semi-permeable membrane, the area for diffusion, and the change in the concentration of solid per unit distance. And basically what the equation says, since usually distance is more or less the same, or it's something that is easily controllable. The concentration gradient is the main driving force for diffusion, and this is great because this is an equation that actually summarizes the behavior of innumerable, like a very large amount of molecules acting randomly, but acting randomly within a certain pattern, within a certain probabilistic envelope. So we are able, to take a chaotic behavior and somehow quantify it, describe it in a quantitative way, which is highly accurate. Now, things get a little bit more complicated if the species is electrically charged. Not excessively complicated, but a little bit more complicated. So the diffusion coefficient, as I said, depends over the properties of the semi-permeable membrane. And this is true if you do have a semi-permeable membrane. And this is important for us in this case because in living organisms you do have semi-permeable membrane, so you need to know what species go through it and which not. However, diffusion is a process that occurs everywhere in the universe, not only in living systems. So actually the diffusion coefficient depends on many more variables, such as the temperature, solvent, interactions between the solid and the solvent itself. So for example, water interacts very strongly with electrically charged ion. The size and the shape of the molecule, the bigger is the molecule, slower it moves. And in case of ions, the density charge, the charge density, which is the electrical charge divided by the atomic volume, which is a function, of course, of the atomic ray. So, for example, sodium will have a higher charge density than potassium. They both have one charge, but sodium is a smaller molecule. And by having a higher charge density, will exert a higher electrostatic traction against the molecules of water, which will form a shell of waters around the ion of sodium. And hence, even if sodium is small, the unit that moves in solution is sodium with its lump, so to speak, of shell water. Well, it's not really a lump; it's a shell, right, of water. It's really cool because within water there are many waters. Water is actually, ironically enough, one of the less understood substances in the universe. It's kind of ironic because it's such an important compound for living things. We are water basically, and we know not much about it. And water can behave very, very differently in different circumstances. And within the body, yeah, you do have the bulk water, which is the water that forms the bulk of it. But then you do have the shell water, you have the superficial water. There are many different. So when you consider the size and the shape of a molecule, you shouldn't consider just the molecule itself, but the molecule with its load of shell water. And of course, the charge, or as I said, the charge. So the movement across barriers is driven by diffusive forces, so by chemical gradients and electrochemical gradients. The distances are very, very short in the sense that the distances we're looking at are, on a small scale between 5 and 100 micrometers. But, actually diffusion occurs all over the body. And even though it can be slow, from between different compartments, between different large compartments within the body, at the cellular scale is a very, very fast occurrence. So of course there are different kinds of barriers, right? So if we're considering semi-permeable barriers such as the plasma membrane, the bilayer phospholipid, and we look at the movement of water across it, we can consider water as, somehow a substance in itself, right? So when we think about the movement of molecules across plasma membranes, we always think about solutes, such as glucose or ions or proteins or amino acids and whatnot. But water itself is a chemical species that actually can move freely. So what's the direction of the movement of water? Is the same as for any other substance. Water moves from the compartment where it's more concentrated to the compartment where it's less concentrated. And so the compartment where water will be less concentrated is the compartment where there is the higher amount of solute. Because if we consider the same volume, if within that volume we only have water in one compartment, for example, in this case, in the left-hand compartment, and then in the other compartment, in this case, the right-hand compartment, we have a combination of water and solutes, obviously the number of molecules of water per unit of volume will be lower. So the concentration of water will be lower. It's also kind of intuitive if you like to cook, because if you like to cook, you know that if you put salt over your, I don't know, vegetables, for example, aubergines, they will release water. It's not magic, it's osmosis. If you put rock salt or fine salt or whatever sort of salt over your sliced aubergines, they will release water. And they will release water exactly for the same principle that I'm showing you here in slide 4 of the fourth part of this lecture. Because the water moves from the compartment with higher concentration of water to the compartment with lower concentration of water. Why it's not going through the aubergines without salt? Because the salt generates a compartment. If there's only air, nothing happens. But it doesn't have to be salt. It can be any solid. It can be sugar. If you put sugar on your aubergines, they will still release water. I'm not sure about their taste, though. So if there is movement of water from a compartment with low concentrations of solute to compartments with high concentrations of solute, then we will have movement of water. And this movement of water will generate pressure. I mean, if you move water, if you move masses of water from one place to another, that will generate pressure. And you can measure this pressure. And this pressure is called osmotic pressure. And osmotic pressure is a physical quantity that can be measured, but it can also be calculated because it depends over physical parameters that we can measure, such as the concentration of solids, the molar gas constant, which is a constant, and the temperature expressed in kelvins. So at physiological body temperature, that will be 310 Kelvin. So once again, you will see that the main driving force of the osmotic pressure is the concentration of solids. So it is dependent on the total number of particles in solution, which is measurable in osmoles, or number of osmoles per liter. Remember, the osmoles is the number of equivalents, not the number of the molecule. Now, if we're talking about glucose, which doesn't dissociate, osmoles per liter and moles per liter correspond. But if we're talking about a substance that dissociates, such as sodium chloride, that in solution will generate two particles, sodium and chloride, then the number of osmoles doubles in solution. For non-electrolytes, a molar solution has an osmolar concentration of 1 osmoles per liter. While for electrolytes, it depends. It depends on how many equivalents they release in solution, which kind of makes sense, right? Because what actually generates the pressure is the solute, right? It's the particle itself. I don't care if sodium chloride outside of solution forms a beautiful looking crystal. Once in solution, it generates two particles. And those two particles are the ones that bring water from one compartment to another. So for 1 osmole of sodium chloride for 1 mole of sodium chloride, 1 mole per liter of sodium chloride, we will have 2 osmoles per liter of sodium chloride. And the osmolarity is the number of osmoles per liter, while the osmolality is the number of osmoles per kilogram of water. So what is the osmolarity of a 0.5% saline solution, given that the molecular weight is 58.5? Put pause here and do the exercise by yourself. Now, I don't know if you've unposed or not. We'll see. But yeah, just try to do it by yourself. If you can't be bothered to do it by yourself, I'm going to do it with you. So the molarity is equal the mass divided by the molecular weight. Well, the number of moles is equal the mass divided by the molecular weight, while the molarity is equal to the number of moles per liter of solvent. So 0.9% sodium chloride means 0.9 weight in volume, which means 9 grams per liter, because 9 grams is 0.9% of a liter. 1 liter is 1,000 grams. 1% of 1,000 grams is 10 grams. 0.9% of 1,000 grams is 9 grams. So I'm just verifying this in my head. Yeah, and the molecular weight of sodium chloride is 58.5 Dalton. So the molarity will be 9 divided by 58.5, which is 0.154 moles per liter. Sorry, yes, moles per liter, which is like saying 154 millimoles per liter. Now, we want to know the osmolarity, and so how many equivalents of sodium chloride are generated in solution for 1 mole of sodium chloride? Yes, the exact answer is 2. So if you want to convert molarity in osmolarity, you have to multiply that by 2. And that will be 308 millimole per, milliosmoles per liter. There's a mistake, which I will correct. So you will not see it once I correct. So the values always need to be corrected by an osmotic coefficient, which depends, for different kind of solutions. For saline, the osmotic coefficient is 0.92. You're given this, you don't need to know it, and so that will be 283 millimole per liter. And so once again, our concentration, right? So this is the plasma ion concentration. What is the osmolarity of these? The total osmolarity is given by the number of equivalents. So in this case, since we're considering every single every single compound and every single particle of solute, we can get the total millimoles per liter that once corrected for the saline coefficient will give us the osmolarity of the plasma and of the interstitial fluid. So the osmolarity of the intracellular fluid is the same of the extracellular fluid. It is isosmotic. And if you will ever work in my lab, you will be obsessed by this because the recordings that we do in my lab are path-clamp recordings where we fill up a neuron with intracellular solution and we bathe brain slices into extracellular solution, which we make in the lab. And these are not very permissive solutions in the sense that the osmolarity has to be exactly spot on, because if the osmolarity is not good, your cell will explode the moment you fill it with the intracellular solution that has not been correctly preparated. Or instead of exploding, it will shrink to death. Now, it will be impossible to make anything small as perfectly as the body does. We can be accurate, but there's a limit to that. So when I can, I always tend to do my extracellular solution a little bit more hypertonic than the intracellular solution. So in this way, the cell, instead of swelling, it shrinks. Now, this became some, like, what I'm saying here became almost like part of my subconscious, I don't even think about these things anymore. I would like for you to be the same, because this is very important. Because the worst that can happen in my lab, if I mess up some millismolar, osmolarity concentration, is that my experiment will fail. If you do it in a patient, they're gonna die. So this is very, very important. The major contributors to the osmolarity of extracellular fluid, interstitial fluid, and intracellular fluid are different ions. So for the extracellular fluid is sodium and chloride, because the plasma membrane is not very permeable to sodium and chloride, and there are higher concentration of sodium chloride extracellularly than intracellularly. While the major contributor of the intracellular fluid osmolarity are potassium ions and any counter ion that is a protein or an amino acid negatively charged. These ions have about a concentration of 140, 150 millimoles per liter. So the major difference between the plasma and the intracellular fluid is that the protein levels are very low in the interstitial fluid. And if they get too low, you get edema, because water will move from the plasma to the interstitial fluid because of low levels of proteins in the plasma. So plasma proteins create a colloid osmotic pressure known as oncotic pressure, because the plasma has a slightly higher osmolarity than ISF. So, fluids tend to move from the interstitial fluid to the plasma. Now, this is very important, otherwise you swell up, you have edema, and you will lose plasma. And if you lose plasma volume, the blood can thicken up. And if it thickens up too much, it loads the heart of work, and that can lead to death by shock. So, for example, what kills people when they get burned is not the burning itself. I mean, if they don't die suffocated, of course, it's not, the burn itself, is the shock, because the burn generates an inflammatory response, which leads to massive edema, movement of fluid from the plasma to the interstitial fluid, and that thickens the blood and that generates the shock. Or people who are anorexic or people who have protein deficiencies in their diet can suffer from decreased oncotic pressure because they have lower levels of protein in their blood, and that leads to a decrease in oncotic pressure, moving water from the interstitium to the plasma, and that leads to the accumulation of fluids in the interstitial fluid and swelling and edema.